Because what you don't know about energy can kill you. Here's Alex Epstein.
Hi, and welcome back to another Power Hour. I'm your host, Alex Epstein. Today, finally, after months and months of requests from our audience, we are discussing hydraulic fracturing. And after months and months of searching for just the right expert, I have him. We have Mukul Sharma, Dr. Sharma from the University of Texas, who's come very highly recommended to me by many people in the industry. And we are going to go through the ins and outs of hydraulic fracturing. So without further ado, Dr. Sharma, welcome to Power Hour.
Well, thank you, Alex.
So there are so many myths about fracking, or there's so many ideas about fracking in our culture, and I actually have in front of me your presentation, which is really great. It's called An Introduction to Hydraulic Fracturing, Facts and Myths, and we'll post that on the website. I thought that before we got to the myths, we'd start with the facts, just so that people have a context and they understand how fracturing works, so then they can understand what's going wrong with the myths. So with that said, let's ask the most straightforward question, which is, what is hydraulic fracturing?
Right. Well, hydraulic fracturing is basically injecting fluids at high pressure into a wellbore to create a crack or a fracture in the rock. And what that does is it allows fluids from the reservoir to flow back into the wellbore more easily.
Okay, could you elaborate on that a little bit, just for someone who's not familiar with, let's say, even a wellbore?
Right. So typically oil and gas is produced by drilling a wellbore into the formation. And after you've drilled this wellbore, you want to produce the fluids from the wellbore. If the reservoir is at pressure, these fluids come out on their own, or you have to actually pump the fluids out using some sort of a pump. In the case of oil and gas from shales or very low permeability formations, you typically drill a horizontal well, which could be 4,000 or 5,000 feet long, and then you create multiple fractures, up to 30 or 40 or 50 fractures in the horizontal section of the wellbore. And then these fractures allow the gas or the oil to have a larger surface area to flow into the wellbore. And this makes for commercial wells that can produce oil and gas at commercial rates.
So you mentioned the issue of horizontal. Could you tell us something about the physical structure of these formations that makes you want to drill horizontally rather than vertically?
Well, there's two primary reasons for drilling horizontally. The first is you want to get a sufficiently large surface area for the oil and gas to flow into the wellbore. And you can accomplish that much better with horizontal wells than you can with a vertical well. So in a typical vertical well, you would need to have a single hydraulic fracture emanating from a vertical wellbore. Whereas if the wellbore is horizontal, then you can actually create these 30 or 40 fractures, which give you a much larger surface area for flow. So that's one reason to do a horizontal well. The second reason to do a horizontal well is the surface footprint that you create with these horizontal wells is a lot smaller than you would with a vertical well. So for example, if you were trying to drain a reservoir that was 1 square mile, you would need perhaps 8 or 16 vertical wells to drain that section. Whereas with a horizontal well, you might be able to do it with 1 or 2 or 3 or 4 wells. So you're reducing your surface footprint by a factor of 4 to a factor of 8.
So the second point, that makes total sense to me. I'm not quite clear about the surface area thing, why the surface area would be larger horizontally rather than vertically for a given section.
Right. So imagine a pipe that's vertical. And if you create a fracture, these fractures, by the way, are always vertical or almost always vertical. So imagine a fracture that goes out vertically from a vertical wellbore. You would typically be only able to accommodate one vertical fracture from this vertical wellbore. If you have a horizontal wellbore, you might be able to accommodate 10 or 20 or 30 fractures along this long horizontal section, because the contact area with the reservoir in a horizontal section could be 4,000 or 5,000 feet, whereas in a vertical wellbore, it might only be 100 feet. So you're increasing the contact of the wellbore with the formation by over a factor of 10 to a factor of 50. And that allows you to place more fractures in the formation.
Okay, so we have these, you mentioned these tighter forms of rock with less permeability, including shales, and that we're fracturing them. What do the fractures look like? How big are they? How wide are they?
So typically these fractures would be about 2 or 3 millimeters wide. They would be about, let's say, 50 to 100 feet tall and about 300 to 600 feet long, typically.
300 to 600 feet long. And how has that evolved over the years? Because I mean, that sounds pretty long given that you're talking about super tight rock. How has that evolved over the years?
Well, over the years, people have gone to larger fractures in vertical wells. In horizontal wells, these fractures have actually typically been the number of fractures being larger, but the size of each of those fractures being typically smaller. So you would perhaps pump 500 pounds of sand in a vertical well. You might only pump 250,000 pounds of sand in a horizontal well. So you create more fractures, but each of these fractures typically is going to be a little bit smaller in a horizontal well compared to a vertical well.
So you're mentioning sand. What's the relationship between the water and the sand, and then the other chemicals that often attract a lot of controversy?
So typically the way the fractures are pumped is you pump what is called a pad, which is typically water or a polymer that goes into the fracture first, which creates the fracture. You follow that up with a proppant stage, which is basically sand or proppant, which is these little BBs of silica sand or bauxite, which are about 0.5 millimeter to 1 millimeter in diameter, which are placed in the fracture to ensure that the fracture remains open after you've stopped pumping. So once you've stopped pumping, the fracture actually closes in on itself. And to keep the fracture open, you need to have these proppant particles placed in the fracture to ensure that you actually have an opening there.
So you mentioned earlier on this issue of a reservoir being at pressure, which means that it's in effect pumping. I mean, the oil is coming up of its own accord. And I've heard statistics like the absolute theoretical maximum that can happen at something like 25%. Is that accurate?
Right. The recovery of the oil and gas from these reservoirs can vary a lot. So, for example, when you have oil reservoirs like the Bakken, which is a shale or a mudstone, if you like, these shales typically produce only about 4% of the oil in place, whereas a conventional reservoir would produce something like 25%. So you're getting much less of the oil out of the ground from these unconventional or low permeability oil reservoirs. For gas reservoirs, the recovery factor could be much higher, could be 20, 30% of the gas in place recovered.
So what would be a percentage for something like the Bakken?
Oh, the Bakken, the recovery for oil in the Bakken is only about 4%.
So does that mean that there's 96% oil left in there that current technology cannot access? That's
correct. There's about 96% of the oil in the Bakken that is not currently recovered with these techniques.
I find the issue of, I want to ask a second about shale and what exactly the term shale refers to. Because in oil handbooks that I've read in the past, they talk about shale as kerogen, which is the ultimate source rock that oil migrates up from. And that's kind of where oil begins. And there's this idea that there's no way to get it economically or energy efficiently from shale. So are there different types of shale? What's the type of shale involved in fracturing?
There are different types of shales. So there are, for example, the oldest shale that we have drilled and produced is the Barnett Shale. And in the Barnett, for most of the production in the Barnett has been natural gas, not as much oil. There is an oilier part of the Barnett, which is now being developed. And the Barnett is typically a fairly hard shale, so it contains a lot of silica and a lot of clay and very little carbonates. So things like calcium carbonate, which is the chalk that we write with the blackboard on. Whereas a shale like the Bakken is really a very calcareous or calcite or calcium carbonate bearing shale. So it has about 30 to 40% of calcium carbonate, only about 20 to 25% of clay, and the rest of it is silica. Silica is what you have in beach sand. So beach sand is silica. Calcium carbonate is like the piece of chalk you write on with on a blackboard. And clay is really a very reactive type of mineral that reacts with water and makes the shale softer. So different shales behave very differently. The Bakken is rich in calcium carbonate. The Bakken is more silicious, contains more silica sand and more clay. The Eagleford is different, also is very rich in calcium carbonate. And so every shale is different. And in fact, within a shale, different portions of the shale can behave differently. So the northern part of the Bakken is different than the southern part of the Bakken and so forth.
So often we'll hear discussions of America has X amount of shale, and it's some insane number, or not insane, but it's a very large number in the trillions of barrels. What is the actual meaning of those statistics in terms of action implications?
So you have to listen very carefully to the numbers that you hear, because there is a number that you can quote, which is the total oil in place, which is the total reserve that you have under the ground. And then there's the recoverable reserves, which actually factors in how much of that oil can actually be recovered. So there's two different numbers that you'll hear about: the total reserves in place and the recoverable reserves. And so the recoverable reserves is the important number to keep in mind, because that's the amount of oil that can actually be recovered to the surface.
Are there any shale deposits that are just unrecoverable, essentially, where you can't get anything out of them because they're too tight?
Yes, there are. There are quite a few shales that do have hydrocarbons in them, where you don't have the kerogen, which is the original biomass that forms the oil, where that kerogen has not degraded into oil or gas. So if the organic material has not formed oil or gas, then you have shales which are fairly rich in organic material, but really don't produce any oil or gas, because you don't have the kerogen that's been converted into the oil and gas.
Wait, could you elaborate on that a little bit? So it's the ones without kerogen that are the problem?
No. So think about it this way. Shales are defined in terms of their extremely low permeability and their clay content. So if they are clay rich, typically 20, 30, 40, 50% clay, and if they have very low permeabilities, then they would be referred to as shales or mudstones. The presence or absence of kerogen further defines them as being either organic shales or shales that do not contain any organics. Shales that contain organics can have kerogen in them, which is the original biomass. Some of the kerogen in some places has been converted to oil and gas. And it's those shales that we are targeting in terms of producing them, right? So the Bakken, for example, is a good example of a shale where a portion of this shale has kerogen, which has been converted to oil, primarily oil in the Bakken. The Barnett, for example, is a case where the kerogen has been converted to natural gas mostly. The Eagleford is an example of a shale where the kerogen has been converted to oil and gas, southern portion and the northern portion being oil and gas, respectively. So you do have these generation of oil and gas that's absolutely essential to making this a resource that can be produced. There are many shales that don't have any organics in them, and there's many shales that have organics that are primarily kerogen, but not oil and gas, right? So not all shales are productive, obviously.
It seems at least intuitive that it would always be easier to hydraulically fracture for gas than oil because oil is denser. Is that true, or is it easier some places to get oil?
No, that is not true. The fracturing has nothing to do with the presence of oil or gas. You could easily fracture oil or gas-bearing shales. The difference is gas is a lot more mobile than the oil. And so it's easier to produce the gas because it has a lower viscosity. And so typically when you fracture the gas shales, you get a much easier production of natural gas because it has a lower viscosity than you do oil. But in terms of the ability to fracture, you can fracture either one just as easily.
What do you mean? What do you mean by fracture either one? I guess with these shales, let's take the Bakken as an example. To what extent is that a gas-bearing shale in addition to an oil-bearing shale?
The Bakken is primarily an oil-bearing shale. So there is some associated gas with the oil, but it's primarily an oil-bearing shale. And that depends very much on whether it's a gas-bearing shale or an oil-bearing shale, depends very much on its thermal maturity. So if it's bedded deeper and hotter, then typically the kerogen is converted into gas. If it's shallower and not as hot, then while the kerogen is cooked at this lower temperature, it converts to oil. So depending on this, its geologic history and its depth of burial and its temperature, you can cook this kerogen into either an oil or into a gas.
Okay, well, since we're talking about cooking, let me ask you just about a more basic question, so that everyone knows. So, how does the original kerogen form, and then how is it cooked?
So the original kerogen is a result of any kind of biomass that accumulated in that location, whether it's from algae or bacteria or animal remains or whatever the organic material was originally that was buried in that deposit. And as it gets buried deeper and deeper, this original biomass gets converted into kerogen, and this kerogen then gets cooked into either oil or gas.
But
sometimes it may not get cooked into anything. It might get cooked to the point where all you have left behind is carbon.
So when it's turning into kerogen, that's a heat process as well, too, right?
It is. It is. So it's the degradation of the original biomaterial into something that is that has lost a lot of its original biomass form and really been converted into something that looks more like an oil and gas deposit or a source rock, as opposed to the original biomass, which was not very well. The original biomass really is what you would see in a compost pile, for example, right? Now imagine that compost pile being buried fairly deep, and then being slowly cooked. As it slowly gets cooked at pressure, high pressure and higher temperature, it gets converted into kerogen, and that kerogen then gets converted into oil. And if it gets buried deeper and hotter, then the oil will ultimately get converted to gas, and there's a gas window. And if it gets even deeper, then even the gas will basically be lost, and you'll end up with nothing but carbon.
So why is the progression always from solid, liquid, gas? How come it starts? How come the bottom of the compost pile always ends up as solid rather than ending up as a pool of oil or some sort of formation of gas?
Oh, because it takes a while for the organic matter to really break down. So you have to break down these very complex molecules into smaller and smaller chains. And as these smaller and smaller chains are created, you end up with a liquid. And if you break them down even further and get into even smaller molecules, then you end up with a gas, which is methane.
Right, but earlier in the process. So so kerogen, I mean, is the source rock is always hard, right? It always starts hard.
When you say hard, what do you mean? Mechanically hard?
Like solid, like.
Oh, yeah. I mean, imagine a compost pile, and so imagine if you were to squeeze it at tremendous pressure, and heat it up, what you'd end up with is essentially material that is hard because of the compaction, and the degradation of the original biomass into smaller molecules basically yields material that looks nothing like the original biomass. It doesn't have any of the complex molecules that the original biomass had. Right? And so you end up with something that is much simpler because all the complex molecules have been broken down into simpler molecules. And that ultimately leads into the formation of these hydrocarbon molecules, things like the alkanes, decane, and so on, which are in gasoline, for example, pentane, hexane, decane, and so forth. And then those are further broken down into smaller molecules, which is the natural gas, as you get to higher temperatures and deeper burial.
I'm just curious, since I have you here, I want to ask, what is the status, do you think, of abiogenic theories of gas or oil? In terms of that there's at least gas in the earth of non-biological origin.
Well, it's possible that you might get something like that. So you might get gas migrating from the there's a lot of debate about exactly what the origin of the gas is and where it might be coming from. Most of the gas and oil that we explore in the sedimentary rocks certainly seems to come from biological sources. I mean, it's conceivable that you might have methane being generated in the mantle of the Earth, below the mantle of the Earth, where you have vents coming in, feeding some of these reservoirs. But I think that's the exception, not the rule.
And would there be any case that oil could have the same thing, or do you think all oil is from organisms?
No, I think it's much more difficult to envision oil being formed that way because at those temperatures and at those depths, you typically would not find any oil. Everything would have been degraded to a gas.
So the temperature as you go down goes up fairly quickly?
Correct.
Okay. Well, I hope the listeners learn from that. I study oil for fun, so it's a big opportunity to have you here. So
well, I hope it's a lot of fun for other people as well. I mean, it can certainly get fairly detailed, and you could go down a rabbit hole in each of these topics. So,
okay, so let's see. Let's go to. I might ask a couple more positive questions later, but I want to go to some of these myths to make sure that we get here. Actually, one more positive question. Where are these shale deposits in relation to groundwater? Because that's a huge controversy.
Right. Most of these shale deposits are much deeper than the groundwater. So most of our groundwater that we source for drinking and for agriculture and so forth is fairly shallow, a few 100 feet deep. Most of these reservoirs where we produce oil and gas are typically thousands of feet deep, 6,000, 8,000, 12,000 feet deep. So I would say that in a vast majority of cases, the oil and gas production is separated from the groundwater by thousands of feet of rock.
Okay, listeners, keep that in mind. Let's start with. I'm just going to go through the myths because I thought you listed them out really well. So I'll take this as a cue. The idea that hydraulic fracturing is a new technique. What's the status of that?
Well, clearly it's not. I mean, those of us that have been working in hydraulic fracturing for a long time, you go to the literature and you see the technology evolution over time. The first hydraulic fractures were done in the 1950s, so over 60 years ago. So there's been a constant development and evolution of the technology, obviously, and there's been over 1 million fracture treatments done in the U.S. Over these years. So it's certainly not a new technology. It's at least 50 years old.
And that raises the question for me because I'm familiar with this fact, but it seems somewhat contradictory with the idea that it's been blowing up in recent years. It's been so dramatic that it's changed the natural gas landscape as we perceive it. It's changed the oil landscape as we perceive it. So is there one evolution that you can pin the magnitude of fracking on now, or is it just multiple things converging?
No, I think you're right. There's really two things that have happened over the last 10 years that have made a big difference. The first is the combination of hydraulic fracturing with horizontal wells. That has really been a transformational technology. Traditionally, hydraulic fracturing was done in vertical wells. In fact, we didn't know how to drill horizontal wells very well until about 20 years ago. So about 20 years ago, people started drilling a lot of horizontal wells and became really good at it. And what they realized was that if you combine this horizontal drilling with the hydraulic fracturing method, and when we first started doing the fractures in horizontal wells, you would typically do 3 or 4 or 5 fractures in these wells. And then somebody said, well, why can't you do 20? Or why can't you do 30? And people quickly realized that if you were to do that, then a lot of reservoirs, a lot of shales that were non-commercial or just not economic suddenly became economic because you could now produce at rates of oil and gas that were commercial. So combining horizontal drilling with multiple fracturing in a single horizontal well, that I think is what made the difference. And I think the large-scale application of this technology over fairly significant areas, both in Texas and in North Dakota and in the Marcellus and so forth, I think people have expressed concern, and rightfully so, about the application of this technology and what the implications are to a lot of the environmental issues that people are talking about.
Going back to this, the technological breakthrough of combining these two, in some sense it can sound as if, well, that sounds pretty easy. Just, okay, go horizontal. Okay, once we can go horizontal, start to fracture. What are the difficulties of A, doing that combination, and then B, scaling it?
Well, there's many difficulties. The first one is to actually have the mechanical integrity of the borehole itself. When you're drilling, originally we were drilling 1,000-foot laterally, and we thought that was pretty good. Today, you don't think twice about drilling 5,000 feet horizontal wells. And we've developed the fluids, the mechanics, and all of the technology to actually make that possible. Back 10, 15, 20 years ago, we didn't know how to fracture these wells in an efficient manner. So it would take us a week to place 10 fractures in a single wellbore. Today, you can do that in a day. And the reason that's possible is developments of new tools and new ways of fracturing these formations and doing it fairly quickly and efficiently. So really the whole technology evolution that's happened is making these processes of drilling horizontal wells and fracturing them much more efficient, much more time efficient, much more fluid efficient, and much more cost effective. So things that would cost something of the order of $10 million before can now be done for a fraction of that cost.
So in terms of just, I think so people realize that my guess is that makes a huge deal in terms of what formations are economic if you can do them. So what, if you look at technology 15 years ago versus today, what quantity of new formations are now profitable to drill that weren't before?
Well, many of these formations that we're talking about now, the Bakken and the Eagle Ford and the Barnett and so forth, were barely economic in the past. The technology has certainly made a big difference, but the price of oil has made a huge difference as well. I mean, remember, a decade ago, the price of oil was a fraction of what it is today. And so the fact that you have increased the cost of oil, the price of oil, and you've reduced the cost of drilling and fracturing these wells, a combination of those two makes oil drilling and fracking very economic. Gas, on the other hand, you can see gas prices have dropped in the past few months, and that has made gas marginally economic in many areas. And so the activity for drilling and fracking is going to decrease as a result of lower natural gas prices. So it's really a matter of economics. I think the technology has now brought us to a point where we've become extremely efficient at doing these things. The question now is, are the commodity prices going to sustain the economics of this operation? And for oil, the answer is yes. For gas, the answer is a qualified yes, because in some areas it's economic and in some areas it's not.
What do you see of the prospects of an international market in this stuff? Because we have much lower gas prices here than, say, in Asia, because we don't have the kind of transport that we do with oil. Of course, it's physically more difficult, but also there are restrictions on terminals. What do you see the next 10 years of that looking like?
Well, that's a very good point. Oil is a global marketplace, and the price of oil is fairly constant across the world, except for this differential we're now seeing between North Dakota and the Brent oil. But natural gas is very much a local marketplace, and so what Japan pays for their gas is a lot more than what we pay for our natural gas. In fact, gas delivered in Japan is priced at about $18 an MCF. Gas delivered in Europe is priced at about $12 an MCF, and gas in the U.S. is $2.50 or $3 an MCF now. So there's a big difference in prices across the world, and so the point that you were making is that the economics is very different in different places.
Yeah, and I would imagine gas producers would want to have more latitude to ship their gas overseas, because right now they're artificially, I don't know artificially, but they're restricted, at least in a physical way, from selling it to people who would bid it up dramatically.
That is correct, yeah. So there is a move towards moving a lot of the U.S. gas through LNG tankers to places outside the US. And the question then is, what is the economics of that, and what is the importance of natural gas to the US in the long run, strategically? So there's questions and debates about energy policy and what is the extent to which we want to export this natural gas and at what price.
In terms of the differential in price, and which is ultimately a matter of the differential in production in here and say different parts of Europe, how much of that is the amount of geological knowledge that exists here versus there, and how much of that is related to property rights?
Well, I think a lot of it is related to property rights and regulations, and also the cost of services. So the cost of drilling a well and fracturing a well in the US is quite a bit lower than in other parts of the world, just because the infrastructure here is very well developed. And so I was in Europe about a month ago, and it costs twice as much to drill and complete a well, and it takes twice as long in Europe to do the same thing that it does in the US. So it is very much, the US is significantly ahead in terms of the cost of doing a lot of the operations that are required to produce this oil and gas.
Yeah, that seems like a really important fact that you don't hear very often, because I mean, if some new regulation is proposed that would make it take 3 times longer, then it seems like it would slow down the progress a lot or make certain things uneconomic.
Oh, absolutely. I mean, if you have regulations in place that in any way delay or hinder a lot of these activities, you could very quickly make these operations uneconomic.
So what, just to give why the issue of delay is so important here, because I don't know if it's always intuitive, what is the cost per day of having one of these things in operation or even in construction?
Well, the main cost is the cost of the rig itself. So the rigs on location cost you money, and how much they cost you, of course, depends on location. It's very, very different. Could be an order of magnitude difference in different parts of the world. But the cost of the rig is, of course, the primary cost that you're paying for. The cost of the people involved, the cost of delayed production, and those are the 3 primary costs that you have if you delay operations and you have to wait on something.
So does the rig cost at all relate to the? I mean, because I guess a delay of imagine you have twice as many delays in the system, and you've got a certain number of targets, then it seems like you would have to build more rigs to ensure that you would, or you'd have to move one to the other, which would have a transport cost. And I think some of that happened in the Gulf post Deepwater.
Well, the cost of the rigs certainly is very important. And if you take twice as long to drill a well, the cost of the well goes up by at least a factor of 50%, if not a factor of 2.
Really interesting stuff. Okay, let's go to the next one. The issue of earthquakes. What is the full context on that?
Well, there's been quite a few studies done on looking at the kind of impact that hydraulic fracturing has on causing earthquakes. And so when people ask me, does fracturing cause earthquakes? My answer is yes. Hydraulic fracturing does cause earthquakes. And in fact, we've measured them. We've measured them for at least 2 decades. And when we hydraulically fracture a well, we can do what is called microseismic monitoring. So we can actually put in geophones and tilt meters and so on and measure on the surface and downhole what kind of seismic waves are being generated as a result of the fractures. And we know that these micro quakes or micro earthquakes are basically about 4 to 6 orders of magnitude lower than anything that you would feel on the surface. So this would be equivalent to a truck rolling down the road and the kind of vibrations that you would feel as a result of the truck rolling down the road. In fact, usually much smaller than in magnitude than that. So we know that we are about -2 or -3 on the Richter scale with the earthquakes that we cause. And we know that because we've measured them. And we've measured them thousands of times on thousands of hydraulic fracture treatments. So it's a fairly well-established science, and there's lots of data in the literature that shows very clearly what the magnitude of these earthquakes caused by hydraulic fracturing is. And it's, like I said, about 1 million times smaller than an earthquake that you would typically feel.
I mean, by the common definition of earthquake, or I think the technical definition, there are just, hundreds of thousands of earthquakes that we don't hear about or notice because it's just a common thing. It seems, I mean, does anything that moves the earth constitute an earthquake?
Well, in principle, yes. In practice, no. I mean, if you ask a person on the street what is an earthquake, well, for him, an earthquake would be something that he or she could feel on the surface, and that would mean that you would have to be about a 4 or so on the Richter scale to really feel something that you could say, oh yeah, something happened. Whereas we are measuring something that's -2, which is on a log scale, that's 1 million times lower in magnitude. And so, it's in principle, it's correct to say that hydraulic fracturing is causing earthquakes, but these earthquakes are so small and so insignificant, and we've measured them so many times that we can say for sure that these earthquakes are of the order of 1 million to 10 million to 100 million times lower in magnitude than anything that you could feel. So I think that while the media can pick up on this and make the case that, oh, this can cause earthquakes, in practice that's just not true.
Yeah, I mean, as far as I can tell, it's just a bias against the fact that human beings are causing it, because there's no upset about all the tiny, -2 Richter scale earthquakes that occur all the time, and no one even knows about them.
Correct. That is correct. Yeah.
Yeah.
And when people claim that it's well documented that injection of fluids into the ground causes earthquakes, and this is true. If you inject water for long periods of time and large volumes of water into areas of the subsurface which contain faults. So, for example, if you were to inject water into the San Andreas Fault, you would enhance slippage of the fault and you would cause earthquakes. There's no question about that. That's been documented. The volumes of fluid that we inject in hydraulic fracturing are a tiny, tiny fraction of the kind of volumes that you would inject that would be required to cause a fault to slip, typically. Most of the time, when we are injecting water for hydraulic fracturing, we are not injecting into tectonically active areas where you have active faults like the San Andreas Fault. So is it theoretically possible to cause earthquakes with hydraulic fracturing? Yes. Has that ever been documented in terms of, has it ever happened and people related hydraulic fracturing to earthquakes? No. And like I said, we've done over 1 million of them in the US, and we have not found compelling evidence of earthquakes that we could feel on the surface, the human beings could feel on the surface, that were directly tied to hydraulic fracturing.
All right. A sort of related criticism, which we partially addressed earlier, hydraulic fracturing contaminates groundwater.
Mm-hmm. Well, I think that groundwater contamination is a very serious and perhaps in some cases a valid concern if you're fracturing shallow formations. The industry has been, I think, proactive about this in terms of making sure that when you are fracturing a formation, that you map where the groundwater sources are and make sure that you are sufficiently removed from these groundwater sources, that you have good zonal isolation between the zone that is being fracked and the groundwater source. Having said that, I think the industry and people who are involved in fracturing need to be very concerned and cognizant of the fact that you can have flow behind the pipe. That there have been cases where fluids have migrated behind pipe. So we should look for better technologies, and we should look for better ways in which we can isolate the groundwater from these deeper horizons. Now, I will say that this communication between these deep zones and these shallow aquifers would be a concern whether you frack or not. So the fact that you drill a well and you cement the casing in place, um, that by itself has the potential for causing communication between groundwater and the deeper zone if the zonal isolation is not properly done, right? So we have to be sure that when we complete these wells, we isolate the shallow groundwater from these deeper zones. And there are many, many, many laws on the books in the states and at the federal level that try to ensure that this indeed happens. So there is testing of wells that is required, there is testing of completions that is required, and so forth. So there are quite a few regulations in place that have been put in place over the last 50 years to try to ensure that this communication between these zones is minimized. Does it happen on occasion? Yes. And can we do better? Yes. I think we should try and do better in terms of isolating these different zones. But I will say that the fluids that are used in hydraulic fracturing are not what I would call hazardous fluids. These fluids contain polymers that do degrade fairly quickly over time. Things like polyacrylamide, guar gum are ones that do degrade over time and are certainly not what I would call toxic fluids. The media claims of using benzene in hydraulic fracturing fluids, I think, is misplaced. Things like bactericides and so forth that are used in hydraulic fracturing. So the chemical composition of the fluids that are used in hydraulic fracturing make these fluids, there is some concern about what the composition of these fluids is. And I think that the industry has been proactive in terms of disclosing what these fluids are and making sure that the public understands what the toxicity of these fluids is. So I think there's been good support for the legislation that was put in place in Texas this year in 2012 for full disclosure of the composition of these frac fluids. I think the industry has actually embraced that, and I think they should, because the public needs to know what kind of chemicals are being injected in the ground as a part of the hydraulic fracturing fluid mixture. And so I think that there has been progress on that front. I think that the law in Texas does indeed strike a good balance between the public's need to know what the chemicals are that are used in fracking and the industry's concern about some of the proprietary chemicals that they use as a part of the hydraulic fracturing mixture. So that balance has to be struck, and I think the Texas law does a good job of striking that balance. And I hope that sort of a law is adopted in other states as well.
It seems like there's a lot of hypocrisy in terms of how much fracturing gets singled out in terms of revealing every little detail and in terms of the amount of weight that's placed on when something goes wrong. Because any technology, you're going to have something going wrong. You could always say, well, theoretically, you should prepare better. But I mean, in terms of the track record, as I understand it, it has a very impressive track record for the most part. Certainly better than, say, the manufacturer of solar panels in China or mills in China. But no one is calling for a full disclosure of all the toxic chemicals that go into these things and making them public. And it just seems like there's a double standard that's ideological.
Right. Well, I think that hydraulic fracturing does have a pretty impressive track record. If this was, I often say to my students that if this was a pharmaceutical trial, it would be an incredible success, because you've gone through 1 million trials, essentially 1 million frac jobs, and with no documented cases of problems associated with this sort of a treatment. So I think that the history of this speaks for itself. I do think that anything that we do as human beings, whether we're walking across the street or flying in a plane or any human activity, has some associated risks. I think the key is to balance those risks with the benefits. And in the case of hydraulic fracturing, I think that there's, in my mind, there's no question that the benefits far outweigh the potential risks.
Yeah, I mean, my own favorite way to think of this is I'm afraid of the dangers of not fracturing.
Yeah, that's a good way of saying it. That's a good way of saying it because ultimately we all do need to provide energy, and that energy mix is important. And in my view, the environmental benefits of using natural gas through hydraulic fracturing far outweigh the environmental risks of drilling and fracking for natural gas. In terms of the carbon footprint, in terms of CO2 emissions, in terms of NOx and SOx emissions, um, in terms of being able to produce a domestic resource, in terms of creating local jobs, in terms of creating revenue for local cities and counties and states. I think that the benefits are incredible in terms of being able to develop this natural resource. Um, and if we want to live in a society where we are going to be consumers of energy, we're going to have to do something. And in my view, drilling and fracking for natural gas is by far the lowest risk way of accomplishing that.
Yeah, I just add to the point about environment. Often I think people think of environment in way too narrow a sense. For instance, does it pollute or doesn't it pollute? But if you look at two of the biggest advances in our surroundings, they would have to be the proliferation of agriculture, i.e. the green revolution, which gives us an environment full of plentiful food. Well, I mean, and what was the other one? A huge amount of eradication of insect-borne diseases, which are 80% of the world's diseases. I mean, we live in a vastly different environment, and those are both, I mean, petroleum or natural gas products. There's no modern agriculture without natural gas.
Right. That is absolutely true. I mean, I think the use of natural gas, not just as an energy source, and oil for that matter, through the generation of all kinds of chemicals that are used in agriculture and so forth, and really in all of our daily lives, I think is absolutely essential. So I think I think everybody would like to see a free and completely benign source of energy. We don't have that. Everything we do in terms of producing our energy supply has some ecological consequences. I think the question is which one is going to have the least. And I think natural gas actually looks pretty good when you do that comparison.
Yeah, I mean, I guess I think of it a little bit differently because, I mean, if you look at our environment by default, the natural environment, absent human improvement, is very rough for human beings. I mean, statistically, probably both of us wouldn't be alive without modern energy-based technology. So you can say there are hazards to our activities, there's hazards to any progress, but the net environmental progress in terms of the quality of our surroundings right now is so far superior to what our ancestors had to deal with.
That's exactly right. And that's the risk-reward balance that you have to achieve. I mean, we all know that there's risks associated with flying in a plane, but we still do all fly in planes, or most of us do anyway. And so, what is the risk and what's the reward? And if the rewards clearly justify the smaller risks associated with doing this, and I think we should do it. And that's the way I think about it.
Yeah. Again, I like the idea of if you're going to think of the risk of doing X, you have to think of the risk of not doing X. You can't just
exactly.
think about.
That's a good way to say it.
I'm just looking at your list. You have the issue of the K in fracking. We've talked about that. We clarified that on a previous episode. I'll leave that one alone because I insist. I use it in op-eds only because you're basically required to.
Yes. In fact, most of the media will use a K in fracking. And if you look at all the technical literature in hydraulic fracturing, when they refer to fracking, they will never use a K. They will always spell it with a C and without the K. But that's just historically the way we've done it in the technical literature. And I can always tell when somebody is is not coming from the technical community of fracking, because they always use a K in fracking.
I've gotten a lot of flack from this for various people. What about just the gasland idea of fracturing causing the water to light on fire, and also as an aspect of that, if I see water lighting on fire, first of all, I know that's been happening forever, but to me the question is how much natural gas do you need in water for it to be really dangerous? So I guess those are my two questions. To what extent is fracking causing it, and then to what extent is that dangerous?
Right. Well, I think in that part of the world, in New York and Pennsylvania and so on, it's quite common actually to have natural gas seeps, which means that you can actually observe in many of these. In fact, in the slide presentation that I've sent you, and on YouTube or places like that, you can actually find places where there's flames, naturally burning flames on the surface. So there's Eternal Flames Park, for example, in New York State. There's a flame burning under a waterfall. And what that is natural gas that is seeping up all the way to the surface. And when it comes to the surface, if you light it up, it'll continually burn for years. And in many of these places, what has happened is ranchers will go in and drill a water well. There's no permit required for these water wells, or there was no permit required for these water wells. And so you'll drill a well, and if it's an area that's prone to natural gas seeps, you will have methane accumulating in your water well. And so if you pump water from that well, you are going to pump both water and methane. And so you'll get the sort of thing that you was shown on the video in Gasland, where you're going to get gas coming up with your water supply because you've drilled a well in an area that is prone to natural gas seeps. And in fact, you can see this. In fact, there's a video on YouTube where a geologist goes out into the field in an area that's prone to natural gas seeps, digs a hole that's about a foot deep, and there's a puddle of water and there's gas bubbling out of it, and you can light it on fire. So there are many places in the world where natural gas will naturally come up and bubble up to the surface, and in those areas you have to be careful where you drill, how you drill, and how you avoid these gases. So I think the example that you saw in Gasland was an example where you had an area that was prone to natural gas seeps, where somebody had drilled a well, and when they pumped water from that well, they got both water and methane coming up with their water. So that can certainly happen, and it's been happening way before fracking was ever done in the area.
I think that's a really profound example, because no one even thinks of the possibility that a water well could cause water contamination. And it's because there is this bias toward any sort of hydrocarbon and anything that's perceived as man-made, whereas water well is just considered pretty benign. You're not doing much to your environment. And yet, I mean, my understanding of groundwater contamination is things that contaminate groundwater are things that are near groundwater. Mm-hmm. Not, I mean, 5,000 feet under the ground. So if your well, if there's a problem in the casing, yeah, that can get into groundwater, but not what's taking place 5,000 feet below.
Right. So I think you have to be very careful when you look at examples like the one provided in Gasland, and really ask yourself, what is the underlying reason for this? Is it really fracking, or is it something else? And I think that when you dig and explore this a little bit further, what you find is that just about every example that I've seen is a result of something that's very easily and plausibly explainable on the basis of what is known geologically about the area, like gas being present in the shallow subsurface, and that gas coming in with the water.
All right. This isn't in your myths list, but I wanted to ask about it. There's the issue of the wastewater and the idea that that's really toxic, and that it's dangerous that there's so much of it, and then where are we injecting it? What's the story on that?
Right. So when you frack a well, about 20 to 30% of the frack water actually comes back. And the question is, what do you do with that water? In most places, you would take that water, put it in tankers, and then dispose of it in a waste disposal site. And so you basically re-inject it back in the ground, right? So this water that comes back is typically pretty rich in salts. So it contains a lot of sodium and calcium and so on. And of course, associated with those salts is some naturally occurring radioactive material, some norms, right? And so typically what we would do is take that and dispose of it in the subsurface. I think the state of Ohio permits reinjection, but the state of New York doesn't. So a lot of the water that's produced from these wells in New York State then has to be shipped to Ohio and is disposed of there. What industry is now doing is actually taking some of this water, treating it, and then reusing it for fracking. And what that does is it does two things. It reduces the amount of water that you need for fracking, and it also reduces the amount of water that needs to be disposed of. And in fact, we're doing some research projects, and other people are as well, on trying to see how you can reuse a lot of this frack water that comes back, right? I will say that the amount of water that comes back is relatively modest by comparison to the amount of water that we produce in conventional oil and gas production, right? I mean, we produce quite a bit of water in conventional oil and gas production without fracking, right? So this frack water is actually a fairly small volume by comparison. But even so, I think we should move towards trying to utilize as much of this water as we can. And that's the direction that I think the industry is going in.
Speaking of water, there's a big focus on just out of context, every frack job uses Y amount of water. Could you put the amount of water these jobs use in context with other human activities that use groundwater?
Right. So typically a horizontal well with multiple fractures will use about 3 million gallons to 5 million gallons of water per well. So let's say you drill 1,000 wells, right? So that would amount to about 3 to 5 billion gallons of water. And that's a lot of water. And so, but if you put that in perspective, so in the Barnett area, for example, we had pulled out some numbers for the municipal usage of water. 3 to 5 billion, well, 3.1 billion is the number we had, was 1% of the municipal usage, actually less than 1% of the municipal usage in the Barnett area, in the Fort Worth area. So even though it seems like a lot of water, and it is, it's a lot of water in areas that are drought prone, particularly in Texas, for example, where parts of Texas are undergoing a drought. The amount of water that's used is small relative to municipal usage, right? So I think when you put volumes of water used in fracking in context of other human activities, it turns out to be a fairly small volume. There was a study done on the East Coast that showed that the amount of water used in fracking in the Marcellus Shale was less than the amount of water used to water golf courses in the states of New York. So, I mean, you have to put this in the right context. Now, having said that, even though those volumes are relatively small relative to municipal usage and so forth, I think it's incumbent on the industry and incumbent on people like me who are involved in research and in hydraulic fracturing to try to reduce the volume of water that we use in fracking. And there's actually been a tremendous move to actually do that. And there's 3 ways in which we actually do that. So one way of reducing the amount of water that's being used in fracking is to not use fresh water, but to use salt water. So traditionally, hydraulic fracturing has been done with fresh water. And that's why we have to source water from aquifers for fracking. What we're doing now is actually being able to use up to 80,000 parts per million of salt and use that water in fracking. And a lot of companies have now moved over from fresh water to salt water. What that allows you to do is to reuse a lot of the water that's coming back that's salty and not have to source fresh water. And so you don't have to go to an aquifer and get fresh water. You can now use salt water, right? And our goal over the next 2 or 3 years is to actually go to even higher salt concentrations. So you can go from 80 to 160,000 parts per million of salt and still be able to use it in fracking.
Wait, right? Doesn't that, I'd be worried about, I mean, I'm sure you deal with this, but corrosiveness issues dealing with salt water.
Well, the primary difficulty in using salt water is the compatibility of the polymers that are used in the frac fluid. So we can deal with corrosion, we can deal with those other issues because it's fairly short time of contact between the steel and the fluids. But what we haven't been able to deal with in the past is the compatibility of the polymer with these very brackish, very salty brines. And so we're working on that problem from a research perspective to see if we can come up with materials that actually work at high salinities. So that's one way in which we're addressing the problem. The second way in which we're addressing it is to actually use less water by using things like CO2 or nitrogen or some other fluid instead of water. So you can use a foam, or you can use pure CO2, or you can use pure nitrogen. And when you do that, you cut your water usage by an order of magnitude. So you use 10 times less water when you do that. And there are places in the country where that has turned out to be a possible solution. And it improves the production from the well as well. And then the third way of trying to reduce the amount of water usage is to recycle the water by putting it through filters and desalination membranes and so forth, and seeing if we can actually use some of the salt water, convert it back into a low salinity water, and then reuse it again. So I think there's plenty of research going on. In fact, research going on in my group in all three areas on trying to reduce the amount of water that we use in fracking. So I think we're moving in the right direction. I think we should try to reduce the water footprint that hydraulic fracturing has, and I think we're making every effort to do that. But I think it's unreasonable to say that hydraulic fracturing uses up all our fresh water from our aquifers. That's just not true, because it's a fairly small footprint in terms of what we use in hydraulic fracturing.
Yeah, my take on it is that you've got a commons problem in water because you don't have any real property rights. And so who's to say that a golf course has a right to it, but a fracturing job doesn't, or vice versa. So that's one thought. Another thought is, it's really, all of these technologies are really cool, and I really admire the industry for working on them. But I'm 100% positive they will not appease the people who dislike fracturing. And I even saw there was some gas-based fracturing solution, and the day it was announced, Greenpeace said this is even more dangerous than water because they can make, with anytime you have a gas, you can make up an explosion. Anytime you have salt water, you can say it's gonna salinate our fresh water supply, and we're all gonna be like people who try to drink seawater on a shipwreck, and we're gonna die. So there's always at least the theoretical possibility of something going wrong. And as long as we define a technology by what can go wrong, instead of actually looking at the full context, including what's virtuous about it, these attacks will never stop.
Well, you're right. I mean, there's always going to be people that are going to say that, this is what can go wrong. And there are things that can go wrong. Like I said earlier, I mean, there's always, any human activity, there's a possibility of something going wrong. I think what we can do is try to minimize what can go wrong by doing the engineering right, and try to do our best in terms of reducing the environmental footprint. And that's all we can do. We can't really ever make the environmental footprint zero. I think what we can do is try to minimize the environmental footprint, and that's the direction that we're moving in.
Well, in terms of the human environment, I like the environmental footprint because it produces a lot of energy for the environment I live in. Right. All right, so we've kept you on an hour. Any final thoughts you want to share with the listeners about this technology, how to think about it, or any references you want to give them?
Well, I think that a lot of these slides that I had sent you are on the University of Texas website and on my website, and they're welcome to looking at these slides. I think anybody that thinks of hydraulic fracturing should think about this in terms of the risk-reward and the benefits that this technology brings to us on an everyday basis. I think when you hear claims in the media, be a little bit more skeptical about what is it that the risk really involves, and dig a little bit deeper and see what kind of what is the real risk associated with doing these activities, and compare those risks with some of the other risks associated with other sources of energy. And I think you'll be pleasantly surprised at how well we're doing in terms of drilling and completing and fracturing these wells. and what a wonderful source of energy this really is, and what an incredible energy revolution this has brought about in the U.S. and the rest of the world actually now.
Yeah, no, I mean, the number one thing I think of when I think of fracturing is it's exciting in terms of what it's doing, for my life, for everyone else's life, for people who don't have a job and can potentially get a manufacturing job since electricity costs are cheaper. It's just, and hopefully soon enough the culture will see it that way.
Absolutely.
So thank you, Dr. Sharma, for coming on.
Well, thank you, Alex. Thanks for interviewing me, and good luck in all your good work.
All right. Thank you. All right. Thanks again to Dr. Sharma for being on the program. Just one quick thought in wrapping up, and I think it's a good thought following last week's Power Hour where we talked about Bill McKibben's pseudoscientific article in Rolling Stone, and that is the issue of context. What I particularly enjoyed about this interview is that Dr. Sharma was sure to put all of these different issues in context and give you the full picture, not at all ignoring any downsides that can occur, but also focusing on the upside and being extremely specific about how things work, what can go wrong, what can't go wrong, etc. And that's in stark contrast to what we were dealing with last week, was a deliberate attempt to distort the full context, to accept you to get a given expect you to get a certain conclusion, but without really giving the full facts. So it's always a pleasure to have a true expert on the show and someone who's focused on context. So I hope you enjoy that. And with that, we're going to wrap up the Power Hour. You know how to reach me, alex@industrialprogress.net. Any questions, comments, love mail, hate mail. Next week, we'll be on with another expert, another great topic. And until then, I'm Alex Epstein. This has been Power Hour.
Power Hour. Life, liberty, and the pursuit of energy. Power Hour. The antidote to shallow thinking about energy issues.